In this video series, we are comparing groups with a single quantitative response variable, and we have been talking about multiple comparison procedures so that we can look at specific questions about those group means, rather than looking at the omnibus question in which are there any differences among the means. It's probably the case that we're going to want to know more specific information about comparisons of the means, and I'm focusing primarily here on pairwise comparisons. I mentioned 3 different methods out of the many methods available that we are going to look at. Those are the Tukey method, the Bonferroni method, and the Chaffee method. And what I have here is the general formula for a confidence interval for psi, that is the population value of psi. Notice that this does not have a hat on it. And what I'm also noticing here that you should notice is that this confidence interval is the same confidence interval that you know about for all the parameters that you've probably looked at in the past. Most especially, you've learned the confidence interval for the mean or for differences in means. You probably learned it for proportions, differences in proportions. And I'm assuming that that's all prior knowledge before you started watching a video on doing this kind of work with K groups where K can be more than 2. And so just to remind you how that confidence interval always looked, you would take the estimate of the parameter, here signified by psi hat, because the parameter is psi. Remember, the parameter is a contrast. We're focusing specifically on pairwise contrast, which means that one of our weights is 1, one of our weights is -1, and all the other weights for the groups are 0. So the estimate of this contrast is the psi hat with a hat on it. And then we add and subtract from that estimate. Notice I have 2 sides to this equation, one in which we're subtracting and one in which we're adding. We add and subtract from this the margin of error. You should recognize this. What is a margin of error? A margin of error is when we take the standard error of the statistic. Here's the standard error of the statistic right here. That's the standard error. And then we multiply the standard error of the statistic by a critical value that we get off of a probability distribution. That is a model of what our distribution would look like for that statistic. And we are using the normal distribution because by the central limit theorem, we know that the that the sampling distribution rather of means, and that's also true of differences in means, which is what we're dealing with contrast, that standard deviation or that distribution of the sampling distribution of those means fits a normal. And so this would be a critical value. Now, when I say a normal distribution for the sampling distribution in means, that's not necessarily where we're going to get our critical value, because if we don't know the population's standard error or standard deviation, so we're using the standard error instead, and that is what we're doing here, then we're going to thicken those tails up a little bit and switch from the normal distribution to a t distribution. So that's the way we've done it in the past with means. But in this particular case, the critical values that we're going to look at actually come from one of 3 distributions. And those critical values are what determines whether you're using a Tukey, a Bonferroni, or a Chaffee procedure. So looking at the confidence interval formula right there, so there's our confidence interval formula. That confidence interval formula is the same no matter which of the procedures we're using. So we're estimating the contrast and we're adding and subtracting a standard error. What's different is what distribution we use to pull out the critical value. The one you're familiar with, as I mentioned, is the normal distribution, or when you're estimating the standard deviation, the t distribution. And that is, in fact, one of the methods that we're going to use. But more generally, what we're seeing here is that we could use one of three methods. We could use for Tukey this critical value, which I'm not even going to take any time explaining. I'm simply going to tell you that we're going to be able to get this in R, and I'm going to use R to show you how to do that here in a moment. But this is from what's called a studentized range distribution. So it's another probability distribution. You could learn about it if you want. Go ahead and do a web search on the studentized range distribution, and you'll learn all about it. The symbol that is typically used for that is Q, and so you'll see that's what I'm using here. And this particular critical value is associated with Tukey's method. So we're going to let R do the dirty work for us behind the scenes, and we're not going to go ahead and learn about the studentized distribution, only to say we know that's what's happening under the hood when we run the Tukey. Then the next one that we have here is Bonferroni's, and Bonferroni's does have something familiar to you. That's from a T distribution. Now, what's a little bit unusual here, we have a T distribution with some degrees of freedom. But what's a little bit unusual here is this piece right here. Let me clear this out. What we're normally used to seeing is that we divide alpha by 2. And once we divide alpha by 2, we can subtract that to 1 to get the upper tail of the distribution. Or you can take alpha divided by 2, and that without subtracting from 1, that's the lower tail. So for instance, if you have 0.05, you divide it by 2 to get 0.025, and you have 0.025 in the lower tail and 0.975 in the upper tail, and that gives you your critical values. So when we use R, for example, we're always using a QT in which we're putting in a 0.975 along with the degrees of freedom. And I don't remember which parameter comes first, the degrees of freedom or the probability. But that's for the normal T distribution. What's happening here, it's not real magical, it's pretty straightforward, is that what we're doing is we're taking our type 1 error rate of alpha, let's say it's 0.05, and we're dividing it by the number of comparisons we're going to do. So if we're going to do 3 different comparisons, we divide alpha by 3. Well, what does that do if you divide alpha by 3? If I take and set alpha prime equal alpha over 3, well, that means that for the first contrast, your type 1 error rate could maximally be alpha over 3. For the second one, your type 1 error rate could be alpha over 3. And for the third one, your type 1 error rate could be alpha over 3. And if you add all those together, that equals alpha. So if you set the type 1 error rate at 0.05 and divide it up by the number of contrast you have, you're keeping the family type 1 error rate at 0.05. Remember, the family is the entire set of contrast. So all we're doing is using a T with alpha prime instead of alpha, where alpha prime is alpha over C. That's all that's different about this. A pretty straightforward way of doing it. You're just breaking up your type 1 error rate into the number of contrasts that you have. The obvious problem with that is if this number here in the denominator C gets really big, then your type 1 error rate for each individual contrast could end up being really small. And as you know, when you have very small type 1 error, you've also reduced the power. And so you could end up having low power. What does that mean in terms of confidence intervals? It means a big critical value, and a big critical value means a big margin of error, and a big margin of error means a wide confidence interval. All right, so the final one, the final method here is Chaffee. And Chaffee's method is handled by taking the critical value that you would use for the omnibus test. So whatever the critical value is that you'd use for the omnibus test, you're going to take that, multiply it by the numerator degrees of freedom. Remember that the omnibus test F statistic has a numerator and a denominator degrees of freedom, or the F distribution rather, has a numerator and denominator degrees of freedom. So you're going to take whatever the numerator degrees of freedom is, multiply it by the omnibus critical value, take the square root of the whole thing, and that is your critical value for Scheffé. And again, the confidence intervals formula doesn't change at all. It's just a matter of which critical value are you putting in. So if I'm putting in the critical value from Scheffé, I'm doing the Scheffé procedure. So we're going to see how to do all of those in R, but before we do that, let me go ahead and clear this out here and talk about each different procedure and what it gives you. I've already mentioned that Tukey's procedure is the most powerful for all pairwise comparisons. So if you're using Tukey's procedure, then you can go ahead and do all pairwise comparisons, but it does assume homogeneity of variance. Remember that we use MSE, that is the mean square error, for our variance from the omnibus, meaning that we're estimating it with all three groups, and therefore we're assuming that all three groups have the same variation. Otherwise, that would not be a good single estimate. We would need to have separate estimates. If you cannot assume homogeneity of variance, then there's an adjustment that we can make with the t statistic. I don't spend a lot of time teaching the adjustment and what it is. I just tell you we can do it in R, because by default, when you do a t-test in R, it does not assume homogeneity of variance. So with Bonferroni's procedure, we do not have to have homogeneity of variance. All we have to do is divide up alpha by the number of comparisons we're doing. And so it's like running a t-test, except instead of using 0.5, you would use whatever your alpha prime is. That is, you would take your alpha and divide it by the number of comparisons, and that's what you would put in for your type 1 error, or 1 minus that for your confidence interval, or your confidence level. So adding comparisons, of course, with this will widen the confidence interval, but it can be used for any kind of comparison you want. It's very flexible. Scheffé's procedure also assumes homogeneity of variance, but you're not restricted to pairwise. In fact, as I've mentioned in a previous video, with Scheffé's procedure, you can do as many confidence intervals as you want, and the critical value doesn't change. Bonferroni, the critical value will change, and you'll get less and less power the more of the intervals you do. That's not true with Scheffé. You fix your critical value at a certain value, and it doesn't matter if you're doing 2 contrast or 100 contrast. That's the critical value you use. And therefore, Scheffé's can be good for exploratory analysis. Not my favorite kind of analysis. If you've been listening to me in my videos, you know that I talk about the necessity for us to move science forward with good theories. But for someone who's just initially looking over some phenomena, collecting data, want to see where differences occur without any prior expectations, you could use Scheffé. Because think about it a moment. What you can do with Scheffé is you can test the omnibus, and when you end up rejecting and you say, okay, there's differences here, you can actually go hunting for those differences. If you recall in the study that we've been looking at with the different worldviews, we have 2 groups, I believe it was individualist and egalitarian, that are the largest difference. You can actually pick that up by hand, say, that's the one that I want to go after. That's the one I'm interested in because it's the largest difference. You can look at the data before you actually decide on your confidence intervals. It almost sounds a little bit like cheating, because normally we talk about how you set everything up before you collect the data. But this works, and it maintains the confidence level, because Scheffé is designed to maintain the confidence level no matter how many different contrasts that you do. Now, if you do not reject the omnibus hypothesis, you're done. In fact, there's a 1-to-1 correspondence. If you do not reject the omnibus hypothesis, there is no confidence interval you can find that will be narrower enough to be all positive or all negative. So if you do not reject the omnibus hypothesis, you're going to have fairly wide confidence intervals, and none of them are going to be conclusive. So we stop when we don't reject the null hypothesis in terms of Chaffee. Now, with Tukey's procedure, you can do it either after the fact, that is, after you've done an omnibus and you rejected the null, you can go forward and do it. But if you're going to do that, if you're going to do the omnibus first, if you do not reject the null hypothesis, just like Chaffee, you stop. If you do not reject the null hypothesis, you stop then and there and don't go forward. However, if you do reject the null hypothesis, you can go ahead and do Tukey intervals, and there's no problem with that. Now, with Bonferroni's procedure, you also could do it after the rejecting the hypothesis, but you have to know how many intervals you're going to do. You can't, unlike Chaffee, you can't look at the various means and say, okay, I want to do 4 of them. If you do that, your probability is actually not going to be what you think it is. So what most people do who are going to use Bonferroni is they skip the omnibus hypothesis and just plan out the comparisons and go right to Bonferroni and do what are called planned comparisons, because we don't need to, we need to know the number in advance, so we might as well just go ahead and look at those specific questions we're interested in. So to summarize, Tukey for all pairwise comparison, Bonferroni for any comparisons, but the more contrast you have, the wider your confidence intervals get. Tukey, the critical value stays the same for all pairwise comparisons. So the confidence interval doesn't matter, doesn't depend on number of comparisons, because you know what the number is, it's all pairwise. And Chaffee, you also have the same critical value for any comparisons you can do, but it is the one unusual procedure in which you can actually look at the data and decide where you're going to make your comparisons. And so the question becomes, do we do the omnibus test or do we do contrast? Exploratory research is seeking differences. So if you're doing exploratory research, remember that the most powerful thing you can do is the omnibus test. So you probably want to do the omnibus test for exploratory research because you want to know, are there any differences at all? Exploratory means just that. You're just wanting to see, what can I find, if anything? So the omnibus analysis is what you're going to do. And then if you do find that there are differences in the means, that is, you reject the null hypothesis of no difference, then if you want to do all pairs, you can do Tukey. But if you want to use the data to help you pick out your confidence intervals, you can do Chaffee. Confirmatory research leads to theory-based hypotheses and specific research questions, so you probably know the specific planned questions in advance, and you probably will want to skip the omnibus hypothesis. And if your questions are about all pairwise comparisons, you do Tukey. But if you have just certain things, both pairwise and complex, that you want to look at, then you do Bonferroni, but remember, you have to know what all those questions are in advance. Now, there is one time in which I would use Chaffee even for planned comparisons. It's very rare, but if I end up finding that the Bonferroni, I have so many contrasts, remember I symbolized that C in the last image, I have so many contrasts that my alpha is getting really, really small. And in fact, my alpha gets so small that my Bonferroni critical value becomes bigger than Chaffee. Usually Chaffee is the biggest one. But if I have so many comparisons it becomes bigger than Chaffee, then it is okay to switch to Chaffee for planned comparisons. The only reason I don't list it here is because typically, because Chaffee confidence intervals can be among the widest, we don't use it for theory. We don't use it for when we have planned comparisons. We're only using it when we want to muck around in the data and see if we can find any differences going on. Usually if you have planned comparisons, C is not that big. That is, you're not planning to do everything under the sun, not from a theoretical basis. That sounds more theoretical, exploratory than theoretical to me. And so in that case, you're not going to have C being very big, and therefore you're probably not going to use Chaffee. So it's really just that one situation is when I would use Chaffee in a planned fashion. Okay, what we need to do in our next video is to look at our R notebook, take the data set that we've been using all along, and see how to do each of these different kinds of comparisons and create the confidence intervals. So I'll see you there.